Time and time again, we've seen that all we need is scale. We've seen that scale actually outperforms any kind of smart heuristic we might try to implement into these models. It's called the bitter lesson. But why does pouring in energy or compute into a system which is based on simple rules like gradient descent, backpropagation, and the reward function lead to so much complexity? Why does this lead to intelligence? And the answer to this actually lies in life itself. If you look all around us, complexity is everywhere. And this complexity emerged because of energy being poured into something what we call dissipative systems in physics. When we look at evolution, when we look at neural networks, these are all dissipative systems. These are open energy systems that take in energy to reach complexity and reach an optimal state. Therefore, systems like these did not need intelligence to be programmed into it. Just like the bitter lesson, we don't have to program intelligence into neural networks, and something intelligent did not have to program creatures to become complex and intelligent. All we needed was a dissipative system with energy flowing into it. But just energy is not enough. We can characterize these evolving complex systems as needing 3 prerequisites. They need a selection procedure, they need mutations in some form, and they need energy. With these 3 things, if it is a dissipative system, it will become complex and it will find its optimum. Let's now go through these 3 things and see how they apply to both evolution and neural networks. See the parallels between the two. And after, we talk about how we can use this intuition to predict the future of AI. Start with selection. In the case of evolution, selection is the competition between animals and the competition between alleles, driving the alleles with the highest fitness to survive and to be given on to offspring. In neural networks, we are selecting for the weights with the lowest loss. We can even see selection in other systems, like in society. When we look at capitalism, for example, it's selecting for the most profit. And by doing so, it's trying to find the best innovators. It's trying to find the best ideas, the best workers. We see emergence from selection all around us. But apart from selection, there also needs to be diversity. Because if there's no diversity, then what can you select from? If everything is equal, you cannot select the best. So we need a mechanism that introduces diversity. In evolution, this is mutations. In neural networks, it might be a bit harder to see, but the mutation is gradient descent. Every time the weights change, they mutate due to gradient descent, and the rate at which they mutate is determined by the step size of gradient descent. Step size being how far does a model walk from one point in the loss surface area to another point in the loss surface area. If the mutation rate is too low, it might never produce a certain organ. A bacteria with a flagell, a organ that propels it forward, it might need like 8, 9, maybe 12 different mutations before it can create a flagell. For these all to happen at the same time is a very low chance. So it's possible that this animal is going to be stuck in a less efficient form for a while. It's going to be stuck in a local minima because its mutation rate is not high enough. But when we up the mutation rate, it could be able to have 7 of the mutations needed and produce a flagell and get to a new, lower minima. And this is the same for neural networks. When we up the learning rate, it's able to get unstuck from local minima and get into a lower point of the surface area. The problem is though, a high mutation rate causes, for example with animals, to get cancers. It causes dysfunction. And so it does with neural networks. A high mutation rate causes it to sometimes be in the best state, be in a global minima, and then jump out of it and get back to a less efficient place. So these systems are very similar, evolution and neural networks. They're similar in selection and they're similar in their mutation. But this doesn't end here. The parallel between evolution and neural networks continues with a very important part, and something that's often overlooked, and that is that we need energy. Energy is the thing that explains why scaling laws are a thing. Because we are looking at dissipative systems. When we pour energy into a dissipative system, a system will reach its optimum state. It will increase complexity to get to its optimum state. And this is what we see with evolution. We pour in energy, and the energy comes from the sun in this case, because without the sun we could not have life. But this sun produces power, and over time, power times time creates energy, and energy is used by organisms. It's used to get this system, in this case the alleles, to get to the highest fitness, or to get to their global minima. With enough time and power, with enough energy, it will get to lower and lower minima. It will find a better and better solution. This is what we have seen happening. Organisms grow more complex and more complex over time. And we see the exact same thing happening with AI. Over time, AI gets more and more complex. Over time, the systems get smarter and smarter. They're reaching their optimum state because it's a dissipative system, because energy moves it towards this. Scaling laws are described as an empirical law, but in the light of dissipative systems, this is not just an empirical fact, it's a physical one. It's a law of physics, just like evolution has created complexity by having a selection procedure, by having mutation, and by having energy. It has increased in complexity over time. And the same thing is happening to intelligence. We have a selection procedure. We are selecting for the lowest loss surface. We have a mutation caused by gradient descent, and it's a system with energy. Energy being the compute. So we have all the ingredients, all the same ingredients as with evolution. We have a dissipative system. We will see an increase in complexity, and we will see a reach towards optimal. Now, besides just performance increasing of these models, we can expect another thing. And that is from looking at the past of these models to looking to the current state, we can extrapolate it to the future state. And what has been the past of these models? The past has been specialistic AI. And we have gone from specialistic AI, like AI that tries to be the best at chess, to AI that's more general, that's good at everything. And there's this upward trend going from specialist to general to more general. And this is caused by compute again. It's caused by energy. Why? Because the energy that a system needs to reach its optimum is defined by its search space. The bigger the search space, the more energy it's gonna need to reach its global minima. With evolution, the search space is endless, meaning it needed a lot of energy. And that's why evolution took as long as it did. And it got a lot of energy from the sun. This is why the complexity of the organisms is so high right now. But with specialistic AI trying to learn chess, the search space is much smaller. The compute we need for it is much smaller. We don't need that much compute to create complexity. And that has been the reason why we've been stuck at specialistic AI for so long, because more general AI, an AI with a more general reward function, would not have worked. We did not have to compute. Therefore, the increase we see in capabilities is due to compute. Surely we needed some ingenuity. We needed to come up with the idea that we could use next word prediction as a way to approach general intelligence. But the bottleneck has not been ingenuity. The bottleneck has been compute, because we could have had the same idea 20 years ago and it would not have worked because we did not have to compute. So as compute increases, we can similarly see how the generality of the reward function increases. And that's just because it's a dissipative system. We can see more complexity arising in the system. So we are allowing it to be able to be more complex. Right now we are constraining it in a certain sense. We're constraining it within its specific architecture, with its specific reward function. We restrict the model from its creativity. For example, when we use reinforcement learning and we're trying to teach a model to walk, and we teach it sub-goals to first move the right leg, plant the foot, then move the left leg, plant the foot. If we constrain it with these sub-goals, it will never learn a more efficient way of walking. Maybe it's more efficient to roll like a barrel, but it will not be able to do that because we constrain it with more narrow goals. Just like we constrained it with just learning chess, just like we constrain it with just learning next word prediction. We are constraining it. Now we have a very general reward function. So you might say, well, what will be the next step? As we increase compute, how can we go even more general than this? For example, instead of asking the model, can you please predict the next word? We can ask the model something closer to what we actually want from it, which is, can you cure this disease? Can you solve science? And the reason we don't do that right now is because if we do that, the way in which the model can reach that goal is, there are so many ways. The search space is so immense. We could not possibly do it. But just in the same way that next word prediction was not feasible a couple years ago, and it is now, it will be feasible in the future to have a more global reward function like this. And even apart from the reward function, we can also look at the architecture itself, because we're constraining the freedom of the model also in the architecture itself. We are using transformer models, but who says that a transformer model is the most optimal model? Why don't we, in the same way that we teach a model to change its weights, also teach it to add neurons, remove neurons, be plastic in this sense, and even change other parts of its architecture? We can add some kind of mutation to the architecture itself, instead of just to the weights. And we can let it optimize for the best architecture together with the weights. And this is not a genius idea that no one ever came up with. Actually, Google did this before. Google has tried this, and they found architectures for visual neural networks that were very efficient, that had top of the leaderboard rankings. But they admit too that they are not applying this because of compute. See, the bottleneck has always been compute, not ingenuity. And ingenuity helps, but we are mainly bottlenecked by compute. And considering compute is so reliably scaling, so reliably increasing, considering we are dealing with a dissipative system with simple rules, and we know that complexity will increase in dissipative system, we are bound to find more intelligence. We are bound to find better performing AI. And we are not constrained to transformer architectures. We are not constrained to this form of learning. The only thing we are constrained by is compute. And as compute increases, we will find better architectures. And we don't even need humans to do that. All we need is energy. And energy will drive progress of AI. And we will be letting it loose to choose its own architecture, to choose its own forms of learning, to choose its own reward function maybe even. This is all something we can predict just from extrapolating, just from understanding dissipative systems, evolution, and the parallel with learning. And in this way, the scaling law is more than just a law for AI. It's actually a reflection of a law of nature described by concepts in physics.